This lesson is on the gradient and level curves. So let's discuss what we mean by level curves. This function generates a surface in 3 space. But if I fix the value, if I fix the height of this, I get a curve. So the set of level curves for this functions are curves of the form 3x squared y plus 2x plus 4y equals c. And I want to answer the following question. So which level curve corresponds to the point 1, negative 2, i.e. the point 1, negative 2 goes through which level curve? We're going to plug in 1 for x, negative 2 for y, and see what we get. And we get that the point 1, negative 2 shows up on the level curve when c equals negative 12. So this is the level curve that I want to graph that corresponds to that point 1, negative 2. Namely, negative 12 equals 3x squared y plus 2x plus 4y. So let's take a look at that. So looking at that level curve, it's here. Now using this app was a little tricky. You'll notice I've put it in as a vector valued function. So I solve for y in terms of x. If you do that in the previous equation, you'll see y is negative 12 minus 2x over 3x squared plus 4. So I just let x equal t. That's how I have this level curve, and then I have the point 1, negative 2. But that level curve is indeed the set of points that satisfies the equation here. Negative 12 equals 3x squared y plus 2x plus 4y. So here's what we claim. We claim that the gradient should be orthogonal to the level curve. So we're going to demonstrate that in this case, and in fact, the gradient is orthogonal to all level curves. If you're at a point that's on a level curve, the gradient at that point will be orthogonal to that level curve. But let's actually see it here. So let's quickly determine the gradient of this function at the point 1, negative 2. Recall in 2 dimensions, the gradient of f is the partial of f with respect to x and the partial of f with respect to y. I tend to prefer this notation, f sub x and f sub y. So quickly doing that, what is f sub x? That would be 6xy plus 2. And what is f sub y? 3x squared plus 4. We're going to evaluate this at 1, negative 2, and let's see what we get. F sub x is negative 10, and f sub y equals 7. So what does that tell me then? Tells me the gradient of f at the point 1, negative 2 is negative 10, 7. And we know that the directional derivative is maximized if you proceed in the direction of the gradient. But I want to show that the gradient is orthogonal to the level curves. So we have the level curve already. Let's go ahead and take a look at this vector. So moving back to the graph, we see that vector negative 10, 7 is very, very large. It's difficult for us to see that, but can we convince ourselves that that's orthogonal to the level curve? I think so. What we often do is we turn that into a unit vector. So divided by its length, which is square root 149, to get a slightly more pleasing picture. So now we have a unit vector that we're working with. And that certainly looks like that is orthogonal to the level curve. And we're going to take a look at another example to identify how this process works. So this time we're going to go ahead and look at the function f of xy equals x squared plus y squared. And maybe you can recognize that this is going to be a paraboloid. So let's examine some of the geometry here. Again, there's our graph. So what are the level curves going to be? Well, C equals x squared plus y squared is the set of all level curves. So there are certainly some that I can do fairly easily, like 1 equals x squared plus y squared, and 4 equals x squared plus y squared, and 9 equals x squared plus y squared, and 25 equals x squared plus y squared. We recognize these are all circles centered at the origin. So let's take a look at that graph. So here we go. This is for c equals 1, c equals 4, c equals 9, c equals 25. And do you see how this is kind of a top-down view of what we had before of this one, right? Looking at this one, we can see the level curves in there, I hope, in terms of how they're working. So our claim then is that the gradient is orthogonal to the level curves. So let's actually find some points. For example, it looks like the point 4,3 is on this graph. We see it? The point 4,3 is on the graph. Now, before we do the algebra, let's think about this geometrically. If we want to go in the path of greatest increase, okay, greatest increase in size, are we going to head towards the center, towards the origin, or are we going to head out? That's the first question I'm going to ask you. And we're going to see if indeed that gradient is going to be orthogonal to that level curve. So let's find out what's happening there. So here we go. F of xy is x squared plus y squared. So the gradient of f is 2x comma 2y. And we were interested in which point? We're interested in the point here, 4,3. We want to see what's happening there. We want to see if the gradient is indeed orthogonal to the level curve. So what is the gradient at 4,3? Would be 2 times 4 is 8, and 2 times 3 is 6. So let's see if we can construct that vector in the direction of 8, 6 at the point 4,3. So looking at that picture, what do we see? Took a little work, but this is that vector, which is much too big. We can make it smaller if we want. And like this is a little arrowhead on the top. And it sure looks like it is orthogonal to the level curve. And indeed, it is in a path as it is growing the fastest. So the next relatively straightforward level curve for us to get would be x squared plus y squared equals 36. So it's moving from c is 25 here to c is 36 here. It wants to get it there the fastest way it can. If it would go this way, it would take longer to get to 36. Do you see that? If it would go this way, it would take longer to get to 36. The most direct route to get the maximum increase of altitude is going orthogonal to the level curves. And that's our basic idea. So what we will say is, we will say the gradient is orthogonal to the level curves. Now, that also works for us in functions of 3 variables. So let's take a look at that. So I have the function f of x, y, z equals x squared plus y squared minus 4z. I can't really graph that because that would require 4 dimensions, but I certainly can find the gradient. What is that going to be? It'll be f sub x comma f sub y comma f sub z, and that becomes what? 2x comma 2y comma negative 4. And this time, the gradient's not orthogonal to a level curve, but it's orthogonal to a level surface. So what is a level surface? Well, the idea is the same. We take any constant c equals x squared plus y squared minus 4z. So let's look at some of those level surfaces. Let's take a look at the graph. Here I have x squared plus y squared minus 4z equals 1. Let me change it to 9. How does that change the graph? Let me change it to -3. How does that change the graph? So you'll notice we have different level surfaces for different constants. Let me go back to 1. This is the one I want to focus on. And I'm curious about what's happening at the point 2, -1, 1. Let me go ahead and add that in. We'll add in the point 2, -1, 1. And do we see that point on the graph? 2, -1, 1. Oh, there it is. We see it. Now I want to look at the gradient to see if the gradient is indeed orthogonal to the level surface at that point. So I want to know, what is the gradient of f at the point 2, -1, 1? 2x, so 2 times 2 is 4. 2 times y, 2 times -1 is -2, and then -4 in that slot. So I want to put this vector on to see if indeed that vector is going to be orthogonal to that surface at that point. So looking at the graph, I put in the vector 4, -2, -4 at the point 2, -1, 1. Is it orthogonal to that level surface? What do we see? Can you believe that that's orthogonal? I'd say that's pretty good evidence, which gives us our conclusion, which is indeed that the gradient is orthogonal to level curves and level surfaces.